And now, just continuing on with what we have in functions. And we have from page 147, okay, and we have just looking at the determination of function values and expressions. And we have for number 44, okay, this problem is going to be in reference to what we have for the given function f of x. And in this one, okay, we have f of x is assigned to be equal to x squared plus 3x. And in the problem, okay, we're looking at trying to determine, okay, just what we're going to have for f of 5. Okay, so for f of 5, okay, so we have the input at 5, and 5 is going to take the place of x. So x squared plus 3x, okay, this is going to translate out to 5 squared plus 3 times 5. Okay, so we have 5 squared is at 25, and 3 times 5 is 15. And for the output, okay, we have 25 plus 15 is equal to 40. So if you had the graph of y is equal to x squared plus 3x, among the many points that would belong to the graph of this function would be 5, 40. 5 for x and 40 for y. Now, looking at what we have for the next item, okay, and we have in reference to the reciprocal function g of x, and in this one, okay, now we have with number 47, okay, so we have the function g of x is equal to the reciprocal of x and in this one, okay, this is probably about the easiest problem in the whole book, okay, because if g of x is equal to 1 over x, well, we have for g of t, only thing we have in following through is that, in effect, we're just changing the input from x to t, and so we have for the outcome, this is just going to be 1 over t. Nothing more, nothing less. And in the case of 56, okay, still writing the coattails, okay, of g of x equal to 1 over x. Okay, so we have in this one, okay, so we have g of x plus h and guess what, we're still looking at the function g of x. So we have g of the input is equal to 1 over the input, and just changing the input from x to x plus h, well, the output is just going to be 1 over x plus h. Okay, now going back to looking at what we have regarding the domains of functions, and we have in the set, now we have for number 100, okay, in parts A through C, okay, now we have the function, okay, we have y of t is equal to 16 minus t. Again, so I had the square root of 16 minus t. Alright, and again we have an even root radical. Okay, so once again we have that in order for the function that we have for y to be defined, okay, we have that 16 minus t, again, because we are working with the square root. 16 minus t cannot be negative. Now it can be 0 and it can also be positive. Okay, so yeah, for 16 minus t, okay, we have this set as being greater than or equal to 0, and looking at solving for the inequality, and again just serving as a backdrop to the interval solution. Okay, so if I isolate the t term. So I can take 16 away from both sides. So here we're going to have that negative t is greater than or equal to negative 16. And if I change the signs at both ends, so if I multiply or divide by negative 1, so if I have like negative 1 times negative t, again, we're going to switch over from greater than or equal to less than or equal. And so for what we will have for the defining inequality, okay, so we have, we're going to have that t is less than or equal to, and we have negative 1 times negative 16, which will be positive 16. And so just looking at what we have now, okay, so we have with t is less than or equal to 16, so we have the number 16, and for less than or equal to 16, so we have with the equal sign 16 is included, and we have from this, okay, we will have a ray that's going to go continuously to the left. And so we have the lower limit, okay, tending to negative infinity. So we have for the domain in this one. Okay, so we have for t is less than or equal to 16, so we have, again, going from negative infinity, and we have approaching and including the value of 16, and the 16 is going to be in the bracket. Right. So this is what we have in the result for part A. So we have the domain, again, going from negative infinity, approaching and including 16. Now, for what we have for part B, okay, now we have, this time we're going from y of t to w of t. And this function, okay, we have set equal to the square root of t minus 16. Okay, and okay, so you have almost the same problem, except we had the t and the 16 switched around. Okay, so again, because we have a square root expression, t minus 16 in itself cannot be negative. Okay, now it still can be 0 or positive. So t minus 16 is greater than or equal to 0. And looking at isolating t, so we have upon adding 16 to both sides. Okay, so we have that t is greater than or equal to 16. Alright, and so just looking at it, illustrating with the use of a number line, and we have with the activity. Okay, so 16 is going to be included in the mix, and on 16, okay, we're going to have, thanks to the equal sign, okay, one is going to be a close point. The rest of the values in t will be greater than, and so there will be a ray that will be going out to the right and approaching infinity. Alright, and so we had the backdrop, okay, to express the domain in interval notation. So we have for the domain, okay, so instead of finalizing or ending at 16, we're going to be starting from and including 16. And so 16 we have the bracket, and again representing the upper limit, which will be approaching infinity, and we have in the parenthesis. Alright, so this will be the outcome for part B for number 100. And for what we have in the case of C, okay, now we have the function z of t, and we have is equal to 1 over the square root of 16 minus t. Okay, and again we're kind of back to that twofold situation. Now again, we have a square root. Again, so 16 minus t cannot be negative. And once again, because we have 16 minus t in the denominator position, okay, so you have that 16 minus t cannot be 0. So it can't be negative, can't be 0. So the only remnant we have, or category, to which 16 minus t can be, is going to be positive. So 16 minus t, whatever we have in the difference, must be a positive value. And just setting up what we have in inequality terms. Okay, so positive means greater than 0. So in the setup, okay, so we have 16 minus t is greater than 0. And if we isolate the t term, so again we have subtracting 16 from both sides. So we're going to have negative t is greater than negative 16. And a bit of history repeating. Again, we're undoing the negative. So either multiplying or dividing by negative 1. We're going to change the direction of the inequality. Okay, going from greater than to less than. And so for what we will have here, okay, we're going to have that t is less than 16. All right, so we have with the number of concerns, so we have 16. T is less than 16, so 16 is not included. But what will represent t, okay, we have a ray that's going to go out to the left of 16 and run continuously in the direction of minus infinity. So we have in the case of the domain, okay, so we have going from negative infinity, approaching but not including 16, so we're going to have parentheses throughout in the interval notation for that particular domain. Alright, now for what we have in the case of number 104, okay, and I tell you what, we'll look at both s of x and t of x, as well as r of x. So just for what we have in the case of 104, we'll look at all of these functions. Okay, so we have with r of x. Okay, so r of x we have equal to x squared minus 4x minus 12. Okay, now here, okay, because we don't have anything like a fraction or an even root radical, that means there's nothing that will keep x from being a 0 or any positive real value or any negative real value. So in this case, there are no restrictions on x. So that means that for at least r of x, yeah, for the domain, okay, so you have the set of all real numbers. And again, in interval notation, you have between negative and positive infinity, and we have enclosed by parentheses. Now for the function s of x, okay, this time we're looking at, in this layout, okay, we got x squared minus 4x minus 12. Okay, and we have all over x plus 1. Okay, now for this rational function, now there is restriction. Okay, and in this one, again, for a fraction, the bottom part cannot be 0 in value. Okay, so x plus 1 cannot be 0. And so this will mean that x cannot be equal to negative 1. And just looking at the development, okay, of how to express the domain in interval notation. Okay, so just again, so if you're to look at it from a graphing standpoint, okay, so you have negative 1 is not included. Okay, so you have a hole, but everything else before it and after it will be in the domain. So just going in both directions. Okay, so we have for this activity, okay, so we have going continues to the left approaching negative infinity, and we have to the right approaching infinity. And so we're going to have for the domain, okay, so you have for the left half, okay, prior to negative 1. So you have between negative infinity and negative 1. So this is for the values of x less than negative 1, and then for those greater than negative 1, then we have for the second subinterval, so you have going past negative 1 and approaching infinity. All right. So that'd be the domain for what we have for s of x. Now for t of x, okay, now t of x is essentially going to be the reciprocal of s of x. So just flipping the ratio. Okay, so we have x plus 1 all over x squared minus 4x minus 12. And in terms of finding out, okay, just what will be restricted, again, because it is in the denominator and not the numerator. Okay, this time it is that we have x squared minus 4x minus 12 disallowed from being equal to 0. So in this particular case, all right, so if that expression cannot be 0, then neither can its factors. So we have in the mix, okay, so we have in factoring, so we have x, let's see, it's going to be x, yeah, have x plus 2 and x minus 6. So if x plus 2 cannot be 0, so we have the x cannot be negative 2, and if x minus 6 cannot be 0, but we have the x cannot be equal to 6. Okay, so we have two exclusions from the domain, and setting up what we have here. So we have with our two excluded values, and just setting up, okay, and doing our bit of labeling. Okay, so we have negative 2, 6. Again, we have both the values are left out. So you have holes located on these numbers, and in terms of the activity, okay, to represent all the other values, okay, so you have for those values less than negative 2, okay, you have array going to the left, approaching negative infinity. And then we have for the in-between values, okay, so we've got those values of x greater than negative 2, and then in turn we have less than 6. And then we have for the final stretch, okay, we have those values of x that will be greater than 6. So you have an array that's going to go continuously to the right and in the direction of infinity. All right. So we have two exclusions from the domain. And so that means that in interval notation, okay, we're going to have 3 subinterval sections. Okay, so looking at what we have here for the domain. Okay, so we have for the segments or sections. Okay, so first part, for the smallest set of values, we have from negative infinity approaching -2. Then we have those values between -2 and 6, but not including either of those terms. And then we have, for the remainder, we have those values of x that will be greater than 6. Okay, so that'll be the makeup for what we have in the domain of t of x and expressed in interval notation. All right, and now just for what we have on page 162, and just sort of touching upon what we had encountered with graphing, as well as the determination of slope. And so we have on page 162, now if we're looking at the slope of a line that passes through 2 points, and we have, in this case for number 28, we have a couple of ordered pairs. Okay, so you have -9, 4, as well as -1, -6. And keep in mind that all ordered pairs are going to be of the form xy. And it doesn't matter which one you have as the first pair and what you have as the second pair. We can place what we have in the order that we see the numbers. So for -9, 4, we can let this be the first set of x and y values. And let -1, -6, okay, be the second set. So we have -1 will be the second x, and -6 will be the second y. And for the slope m, again we have equal to y of 2 minus y of 1. Then we have all over x of 2 minus x of 1. And just substituting in accordance. Okay, so we have y of 2 at -6. We have minus y of 1, so this is going to be -4. For x of 2, minus x of 1, x of 2. Okay, so we have at -1. Then we have minus x of 1, which is going to be -9. Okay, so we have -6 minus 4. Okay, that will automatically become -10. -1 minus -9. I'll just kind of draw this out a little bit further. See, we're going to have -1 plus 9. So we have -10 over 8. And we have, with the ratio, this would come out to -5/4. Okay, so the slope is a negative ratio where we have -5/4. So you have like a pattern, like in terms of motion. If you were to read in order from left to right, you'd be looking at going down 5 units and shifting over to the right 4 units. Okay. Now, for what we have in the case of 33, okay, we have with the set of ordered pairs. Okay, we have fractions in the mix. Now we got in this one. Okay, so we have 3/4 and 6 presented first, and then we have 5/2 and 1. And just taking what we have here, again keeping in mind that all ordered pairs are the form xy. So for 3/4 and 6, we'll let this be the first set of x and y values, and let 5/2 and 1 be the second set of x and y terms. And so for the slope in this case, same formula, and if we were to substitute accordingly, so we have for y of 2 minus y of 1, y of 2 we have at 1, minus y of 1, so we have -6. And for x2 minus x1, so we're going to have 5 halves minus 3/4. Okay, so you have a bit of a complex fraction. Now we have 1 minus 6. Okay, so we have -5 at the top. Now for what we have on the bottom, okay, now if I take the difference between 5 halves and 3/4, you can write 5 halves as 10/4 minus 3/4. Now we still have -5 at the top. Now 10/4 from 5 halves minus 3/4. This is going to come out to 7/4. Now we have a complex fraction. And what's going to happen here is that if you're looking at dividing by a fraction, you're going to multiply by the fraction's reciprocal. So we have a -5 divided by 7/4. So if I undo the division, so I'm going to remove 7/4 from the bottom and flip it. And so we're going to have for the slope, okay, you have -5, or read it like -5/1 times 4/7. And so we have for this outcome, we're going to have -20/7. And so just like what we had with number 28, we're going to have another non-integer slope value. All right, now just looking at now where we have in the illustrations, and we have starting out, okay, now in the case of 39, okay, so we have so if you kind of look at the grid patterns in the text, okay, so I'm just going to insert, okay, the x-axis as well as the y-axis. Okay, and so we're going to have like, let's say just a couple of key points here. Okay, so we have 0, 2, and 3, 1. And if I apply, okay, so you have a line going through these points. Okay, and a way you could look at this, okay, so we can say that x1, y1 be equal to 0, 2, and x2, y2 be equal to 3, 1. Okay, now if you notice there's a downward trend if you read in order from left to right. Okay, so the slope is going to be a negative quantity. So if you go through the slope formula route, so we have with y2 minus y1, so your y2 is at 1, y1 we have at 2, x2 minus x1, x2 is at 3, x1 we have at 0, and guess what, we have 1 minus 2 is -1, 3 minus 0 is 3, so the slope is equal to -1/3. Okay, and again, another way that you could look at this, okay, if you were to read the graph, is that you could take a bit of a triangular formation, So you have just a downward trend. Okay, so you have del 1 and going over to the right 3 units. So you have the ratio of vertical change to horizontal change. And numerically, down 1 translates to -1, and over to the right you have shifting over positive 3 units. So regardless of whichever approach you take, okay, we have the slope is equal to -1/3. And in the case of 42, okay, now we have in this particular setup, okay, so if I just reapply the X and the Y axes, and it looks like looks like we're going to have the line to run between 1 and 2. And this line we're going to have running straight up and down. Okay. And what you could do is that you could or just knowing that the line is vertical, you could just kind of go ahead and arrive at the slope. Or way you could look at this, okay, so you can say it's something like 3/2 for X and 1. We can let this be the first set of X and Y values. And we'll say we have 3/2 and 3. Will be the second set. And so for what we'll have in the case of the slope, we have y2 minus y1 all over x2 minus x01. Guess what? y2 minus y01. Okay, so we have 3 minus 1. x2 minus x01, guess what? We got the same values in x. So in this case, we're going to have the slope to be undefined. So this is going to signal that the type of line we're dealing with is vertical. Okay. Now I had mentioned yesterday we will be looking into various types of equations, some of which, or many of which, we're going to have the slope as the foundation. And one of which, okay, we're going to have what will be regarded as the point slope form of a linear equation. Okay, and so for what we have, let's say, in the setup and the point slope form, okay, this is going to be kind of like a backdrop to yet another type of linear equation. And let's say that the point slope equation of a line with slope m that passes through 2 points. Again, for these 2 points, okay, and just like in the slope formula, okay, well, we will again designate as x01, y01, and x02, y02. Is going to be, now for the point slope equation, okay, we're going to have, now we normally say x before we do y, but this standard layout is going to have y terms at the front, okay, and tell you what, let me do this way. So you have the point slope equation of it passes through. So let me start out with just 1 point. There is a version that's going to have 2 points. And so we have, it's going to pass through a point, x01, y01. It's going to be whereupon we have y minus y01 is equal to the slope m times the quantity of x minus x01. So you got y minus y01 is equal to the slope m times the quantity of x minus x01. Okay, now for this y that we have here, so for isolating y, so this is going to be our point slope equation. And isolating y will lead to what's going to be referred to as the slope-intercept equation. And for this particular form, okay, so we're going to have that y is equal to mx plus b. Okay. And for what these characters will represent, okay, so we're going to have that m is the slope, and that constant b so have 0b, or y equals b is going to be the y-intercept. I believe that the textbook stresses more the order pair 0b, for the y-intercept, whereas I think Alex stresses more the y equals b aspect. Okay, now let's say that if we have just some cases here, just to kind of tie in together the point slope and the slope intercept equations, and let's say that Now say for these cases here, okay, say if I were to determine the slope-intercept equation, and say we have given, okay, so have now m, the slope, is equal to 5, and a point through which it is going to pass. We have x1, y1 is equal to -1, -2. Okay, now in the backdrop to this, okay, so again we have the point slope formula. Again we have in the setup, so we have y minus y01 is equal to m times the quantity of x minus x01. Okay, now again we normally say x before we do y, but we got the y expression out the front. So if I were to substitute accordingly, okay, so you have for y minus y01, your y01 is going to be at -2. And for the slope m, which we have at 5, you have times the quantity of x minus x01. So you have x minus, and your x01 we have at -1. And just to kind of clean up what we have here, okay, y minus -2 becomes y plus 2. And we have equal to 5 times the quantity of x plus 1. Okay, now so for what we're going to have in this particular at this particular stage, okay, now this y plus 2 equal to 5 times the quantity of x plus 1, okay, that is going to be the point slope equation. So if you have like a run-in with an ALEKS problem where it says to write the point slope equation of the line described here, this is going to be y plus 2 is equal to 5 times the quantity of x plus 1. And now in the crossover to the slope-intercept equation, this is where you're going to isolate y. So you have y plus 2, 5 times the quantity of x plus 1. So this is going to be 5x plus 5. And isolating the y. Which can be done by taking 2 away from both sides. And so we're going to have that y is equal to 5x plus 3. And for what we're going to have for this particular part, okay, so this outcome, again, that is going to be the slope-intercept equation. And this time around, okay, with the details, okay, so we're going to have from 5x plus 3, you got your slope m is equal to 5. Now we have for the y-intercept, we can say we have, okay, this 3 here, your y-intercept, if you put in coordinate fashion, your b is represented by 3. So you can say we have 0, 3, or that y is equal to 3. Okay. So we have, in this particular regard, okay, so have 0, 3, or y is equal to 3. And now, another case here, now let's say if we have a negative slope, and the point through which the line passes will be 2, 6. Okay, so we have one point that is provided and the slope is given. So y minus y1 is equal to the slope m times the quantity of x minus x01. So we have in substituting. So again, we have y minus y01. y01 is represented by 6. And we have equal to, now m we have at negative 4. And we have times the quantity of x minus x01. And again, x01 is going to be at 2. And so, again, we have y minus 6, negative 4 times the quantity of x minus 2. And so, just this part here, this example, that's going to be the point-slope equation. And then we have, in developing the slope-intercept equation, okay, so still have y minus 6, and to the right, if I distribute, then we have negative 4x plus 8. And then isolating y, okay, so adding 6 to both sides. We're going to have that y is equal to negative 4x plus 14. Again, so that's going to be the slope-intercept equation. And again, so we have the slope is equal to negative 4. And the y-intercept. Okay, this time, if you put this in coordinate fashion, we'll have 0, 14, or y is equal to 14. Okay, and again, I'm going to go with a special kind of situation here, but before I go, let me pause right here and just mention something. Okay, so in the first case, you can sort of test out how consistent this slope-intercept equation is with what is provided. Okay, so you had the slope is given as 5. Okay, and now for the x and the y coordinates. Now this represents all possible values of x and y in this equation, but if we were to draw out specifically this particular point, now you want both sides, okay, to be equal to each other. So if you have like y at y01 to be negative 2, so left hand side of the equation is at negative 2, and we want the right hand side of the equation to also be at negative 2. So if I set x to x01, which we have at negative 1, well, 5 times negative 1 is negative 5, and negative 5 plus 3 is negative 2. Negative 2 is equal to negative 2, so this will check out. And for negative 4x plus 14, so if I have like y01, our x and y values given happen to be at 2 and 6. So if I take this 6 to represent y, and 2 to represent x in this equation, we need both sides to equal each other. And again, we have it's already baked in that the slope is negative 4. So looking at the consistency, so left hand side of the equation is 6. And then we have to the right, negative 4 times 2 is negative 8. And negative 8 plus 14 is also at 6. 6 is equal to 6. So that equation also will check out. Now, let's say that if we do not have the slope provided, and we're still looking for the slope-intercept equation. Now let's say that the line runs, let's see, and say it's going to run through 2 points. Okay, and if you notice, okay, we don't have the slope given. Okay, we're going to have to find out, okay, what that is going to be. And what we can do here, so we have to find out, okay, what the slope is going to be. Okay. You can designate either order pairs, the first and the second. Okay, but just keep in mind all coordinates will be inside the parentheses in the form of x and y. So we'll say we have 0 and 6 will be the first x and y values, and 2 and 12 will be the second set. So if we substitute accordingly, so we have with y2 minus y01, so we have 12 minus 6, x2 minus x01. Okay, so that'll be 2 minus 0, and here we have 12 minus 6 is 6, divided by 2, and so we have that the slope is equal to 3. Okay, and now in the route to which we're going to be utilizing the point slope equation to get to the slope intercept equation. Now you have your choices. Now you can just kind of hit the reset button in terms of what's going to represent the x1, y1. We now know what the slope is going to be, and you can choose 0.6 or 2.12. For x1, y1 in the point slope setup. There's no wrong choice in this one. Okay, and tell you what, we can go with, we'll go with 0.6. And again, just with the point slope equation setup, again we have y minus y01 is equal to the slope m, and we have times the quantity of x minus x01. Okay. Alright, so you have y minus y01, so we have here your x1 is 0, y1 is at 6. I'll do here, I'll just do a little bit of color coding. So you have y minus 6. You have is equal to m. Now m is determined to be at 3. You have times the quantity of x minus 0. And here we have y minus 6 is equal to 3x. And getting the y term by itself. So we'll have that y is equal to 3x plus 6. Okay, and I would just mention with this part here, okay, that's going to be the point slope equation for that version, having chosen 0.6 to work with. And this outcome, okay, so this is going to be the slope intercept equation. Again, so we have that the slope is equal to 3. And we have for the y-intercept, well, guess what? Y-intercept is going to be that first point that was given. So you have 0.6 or y is equal to 6. Now, one might ask, okay, what about the 2.12? If I had chosen 2.12, 12 for y01, 2 for x01, I would still come out to the same equation. And in fact, both of these points should test out for this equation. So we have with y at 6, x at 0, 6 is equal to 3 times 0 plus 6. 6 is equal to 6. Now, if I have y at 12 and x at 2, guess what? Left-hand side of the equation is at 12. And to the right, I have 3 times 2 is 6. 6 plus 6 is 12. So that will check out also. Now, in looking at what we have in the setup, and if we have just regarding intercepts, I had mentioned y-intercept. Okay. And in the book, there's really no clear-cut pathway, like in terms of going from the slope to the slope intercept, and then somewhere along the line, there's like determining x and y intercepts. It all gets kind of mixed up in the bunch. Now for this part, okay, so if I have in the determination of x and y intercepts, now for x-intercepts, okay, now the general coordinates, you're going to have x0. And each x-intercept is going to be location. Where the graph crosses or touches the x-axis. And just a little bit of inversion in the language now for the y-intercept. So when you hear a slope-intercept form, that intercept is in reference to the y-intercept. Now the coordinates you would have in the general fashion, okay, so you have 0y. So you have location where the graph crosses or touches the y-axis. If you notice in the setup, okay, what you would do in the case of an equation, so what happened here is that you'll be looking at, say for each x-intercept, you're looking at setting y equal to 0 and solving for x, whereas we have for each y-intercept, we're doing it the other way around. So you're looking at setting x to 0 and solving for y. Got a little bit ahead of myself. So for each x-intercept, you're setting y to 0 and solving for x. And just a couple of cases here. Okay, so if you're looking at determining the x and the y intercepts, now we'll say we have, as the first case, we'll have a linear equation whereupon we can say we have 2x plus 4y is equal to 12. So if we look for the x-intercept first, so again we have with the general coordinates of each x-intercept, we will have x and 0. Okay, so again for each x-intercept, so you're looking at setting y equal to 0 and solving for x. So here we have 2x plus, that should be 2x plus 4y is equal to 12. There we go. So you have 2x plus 4 times 0 is equal to 12. So after substituting 0 for y, okay, we have only the x term 2x left over. So you have 2 times x is equal to 12. And so we have the x is equal to 6. So the missing coordinate x is no longer missing for it. It is now determined, okay, to be at 6. So we have for the x-intercept, the location we'll have at 6, 0. Now for the y-intercept, again, the general coordinates we have at 0, y. So we're now, in terms of solving, we're working with the same equation. This time it is x that will be set to 0 and y which will be solved for. So again, 2 times 0 is 0. So left hand side exclusively has 4y. And we have 4y is equal to 12. And with division by 4 we have that y is equal to 3. And so with the value of y determined, the y-intercept 0y in general is now going to be specified as the point 0, 3. So we're going to have, in effect, just kind of doing a rough sketch here. So again, we have y-intercept as 0, 3. And x-intercept at 6, 0. Then we have in connecting the dots. Okay, so this line goes through. Again, this will be all of the combinations of x and y, such that 2x plus 4y is equal to 12. Okay, so you have your x-intercept at 6, 0, y-intercept we have at 0, 3. Okay. Now let's say, now for this fundamental set of fundamentals here for determining x and y-intercepts, they can apply to linear equations as well as nonlinear equations. And in fact, if we have, say, a nonlinear equation, if we have something like x squared plus y squared is equal to 16, now I'm looking for the x and the y-intercepts. Again, both scenarios, I'm starting out with the same equation. Okay, now for the x-intercepts, again, you're setting y to 0 and solving for x. Whereas with the y-intercepts, I'm setting x to 0 and solving for y. Okay, now with the x-intercepts, the setup, I now have the x squared is equal to 16, whereas for what we have in y, we have y squared is equal to 16. And if we apply the square root property of equality, so you have x equal to plus or minus, okay, the square root of 16, well guess what? We have the y is equal to plus or minus the square root of 16. Then we have x at plus or minus 4, y likewise. We have plus or minus 4. So that means that we had the same values for x and y, but in terms of how we identify in coordinate fashion all the intercepts. It's going to turn out that for the x-intercepts, we have 4, 0 and negative 4, 0. And for the y-intercepts, there's now the x-coordinate, that is 0, so here we have 0, 4, and also 0, negative 4. And just in the case of the layout, and we have for this figure, so you have with the intercepts, okay, we have on the x-axis, the x-intercepts have negative 4, 0, 4, 0, y-intercepts, we have on the y-axis at 0, negative 4, and 0, 4, and of course, this is going to be the graph here, and this equation is going to represent a circle that's going to have a radius of 4, okay, and of course, if you're looking at an equation like this, and this is like Math 172, that if you were to know that it's a circle and not a diamond, let's say, you'll be looking at plotting other points, you know, like x equals 1, y is equal to square root of 15, that's, or like close to 3.9. Okay, so you had just that little bit of interpolating and extrapolating that is in the mix. Okay, so this another case of the determination of x and y intercepts. Okay, now just kind of going back to what we have in reference to dealing with what we have regarding equations, and we have with the slope and the y-intercept. We have on page 162, and just continuing on with the set that we have for number 52. Okay, now you're looking at translating given equation that is in standard form and finding out just what the slope-intercept equivalent is going to be. So again, we have just the object. Okay, we have y is equal to mx plus b. So I'm going to translate what I have here in terms of y is equal to mx plus b. Okay, so we have writing an equation in terms of a specified variable being at y. So if I get, first of all, the y term by itself, so I can take 3x away from both sides. So we have negative y is equal to negative 3x plus 6 and you can just change the signs throughout, either specifically multiplying or dividing by -1, or just, again, just kind of like just mentally changing the signs throughout. In other words, like what was negative becomes positive and vice versa. So if I apply both sides the multiplication by -1, so we had that y is equal to 3x minus 6. Okay. So that is going to be the slope-intercept equation. And for what we have here, okay, so we're going to have that the slope is equal to 3. And for -6, now I have that b is equal to -6. So that's going to signal that the y-intercept, we can put it either in coordinate fashion at 0, -6, or y is equal to -6. Okay, so this will be your slope-intercept equation. Now just for what we have in the case of graphing, what we have here. Okay, so you have a y-intercept of 0, -6. Okay, so you have plotting, so you have y-intercept at 0, -6. And with the slope m equal to 3, again, you can have a trend of up 3 units and moving out to the right 1 unit. Okay, so if I were to take, say, proceed from -6, so I have like going from 0, -6, so if I go up 1, 2, 3, and go out to the right 1 unit, and do once more, so they have going up 1, 2, 3, and out to the right 1 unit. Now just connect the dots here. Again, so there's going to be a triangular pattern. So you have up 3, right 1, up 3, right 1. So among the other points, you have like from y at -6, so you have y at -3 shifting over 1. So you have like 1, -3. And if I shift upward 3 units and then go to the right 1 unit, have another point which will be at 2, 0. Okay, so this line here will represent all the combinations of x and y values, such that 3x minus y is equal to 6. So if you notice, you got 3 times 0 minus 6 is going to be in this case, right? So you have 3x minus negative 6 comes out to 6. 3 times 1 is 3, minus negative 3 comes out to 6. 3 times 2 is 6, minus 0 comes out to 6. And just to kind of take this one more, see, kind of envision going up 3 and to the right 1 unit. So 3, 3 will be another order pair. Like 3 times 3 is 9, minus 3 comes out to 6. So if you go up 3 to, then go out to the right 1 unit, you're still on that particular line. Okay, and now for what we have, another case here, for the determination of what we have for the slope-intercept form. And there'll be a little bit more of a modification that is going to be done. And we have for number 62, we have in the form of fractions, whereupon we have x over 3 plus y over 4, okay, is equal to 1. Okay. And again, I want to express this equation in the form of y is equal to mx plus b. And I want to get rid of the fractions, so I can just multiply everything out by the least common denominator. In this case, smallest number that both 3 and 4 will go into will be 12. So if I multiply everything out by 12, okay, so for what I have here, okay, so you have 3 will go into 12 4 times, so we've got 4x. For the next term, 4 will go into 12 3 times, and multiplying by y, so you have 3y. And we have is equal to 12. And we have for 4x plus 3y equal to 12 if I isolate the y term. So you have taking 4x away. So you have 3y is equal to negative 4x plus 12. And we have upon dividing everything out by 3. So it's going to follow that y is equal to negative 4/3 of x plus 4. Okay, so just for the details, okay, so you had the slope equal to negative 4/3. So if you were to read, okay, so this would be kind of like going down 4 and shifting over to the right 3 units. And with the number 4 here, okay, we have with the y-intercept, so you have 0, 4, or that y is equal to 4. And just taking kind of a bit of a quick visual on this one. Yeah, I know the graphing does get a bit tedious. Okay, so we're starting from, let's say, the y-intercept, so you have it 0, 4. Okay, so with the y-intercept, okay, at 0, 4, And if I have a triangular pattern, okay, it's like down 4, right 3. Okay, so we have in the follow through, so we have going down 4, so from y is equal to 4 to y is equal to 0, shift over 3. So I have 3, 0. And if I shift down 4 units and go over another 3 units, so we have 6, negative 4. So y goes down 4 units at a time from 4 to 0 to negative 4. And x proceeds 3 at a time from 0 to 3 to 6. And then just connecting. Let's move this here and do a little modification. Okay, so for this particular line, okay, so this is going to represent all the combinations of x and y that will belong to this equation, which you have x over 3 plus y over 4 is equal to 1, or 4x plus 3y is equal to 12. And also in the slope-intercept terms, again we have y is equal to negative 4/3 of x plus 4. So you have 3 different ways of saying the same equation, but they all represent the exact same line and the exact same points. All right, and just some remaining items here. Okay, and just so we've gone from looking at properties of individual linear equations, and if we kind of cross over to a pair of relations that exist in the case of linear functions, and we're going to have say for parallel and perpendicular lines. And I'm just going to do a kind of a mini lesson on this. Now for parallel lines, okay, now parallel lines, okay, those are going to be distinct lines. Distinct as in they're not the same lines. That are going to have the exact same slope. And will never intersect. Okay. So you have different lines that they got the same slope, they have the same kind of motion. They have like one line directly above the other, and the process, like in terms of where they're heading, the manner of behavior will be identical motion-wise, and so they'll never come to a meeting point. And just examples of parallel lines. And we can say we have something like y is equal to 4x plus 3. And y is equal to 4x minus 7. So you're going to have for both of these lines, you're going to have the same slope. Both of these lines are represented by equations that are presented in slope-intercept form. If you notice for both of these, we have m is going to be at 4, so you got the same slope, m is equal to 4. And so we have that the lines are going to be running parallel. And you can just kind of use this symbol for shorthand for parallel, like a sideways 11. Also, you can say we have, another case, we can say we have y is equal to negative 7 halves of x, and y equals negative 7 halves of x plus 9 and we have the same slope at negative 7 halves. Again, both of these equations are conveniently placed in slope-intercept form, and whatever is next to x, that is going to be the slope. And again, these lines are also parallel. Now, in the case of the other type of relation, okay, parallel lines have going in the same direction, but never coming to a meeting point. For perpendicular lines, now those lines are going to meet. Those lines are going to meet at a right or 90-degree angle. And in terms of how they were able to do that, it'll be where we had the slopes, or the slope values. Are going to be opposite sign reciprocals. Now what this means is, like, if I had like the slope of the first line times the slope of the second line, we had the product to end up at -1. Now say if we're looking for lines that run perpendicular, say I start out with y is equal to 4x plus 3. And if I have like y is equal to some value times x minus 7. Okay, now I need the right coefficient in front of this x in order for the lines to be perpendicular to each other. Okay, so you're going to have, again, the slopes of perpendicular lines are going to have opposite sign reciprocal values. So think of like 4. Got positive 4. As a fraction, positive 4 could be written as 4 over 1. And if I take the opposite sign and then take the reciprocal, so I'm going from a positive to a negative, and then flipping 4 over 1, this is going to be 1/4. And so we have, with the opposite sign reciprocal, this is going to be -1/4. So we have -1/4 of x minus 7. So you're going to have like m1 times the second m. So you have 4 times -1/4. And the slopes are opposite sign reciprocals, and so in this case these lines are going to run perpendicular to each other. Okay. And just a little bit of shorthand, you could represent perpendicular like in the form of an upside down T. And we'll say just kind of borrowing from the setup that we have from the second case of parallel lines. Say y is equal to -7 halves of x And if I form the right coefficient in front of this x for these lines to be perpendicular to each other, so here I'm going from a negative to a positive. And then I have 7 over 2, reciprocal of 7 over 2 if I flip. So this is going to be 2/7. Okay, so I'm taking the product of the first and the second slopes. First line would have slope of -7/2. Second line would have slope of 2/7. And you can cross multiply, or you got like -7 times 2, it's -14. 2 times 7 is 14. And again, the product of the slopes will go to -1. And so this pair of lines will also be perpendicular in fashion. The Alex homework section 1.3, that will be due Saturday evening. Okay, and you have 1.5 will be due Monday. And then I got the video simulations available. And again, go ahead and be looking into page 176, number 6, 12, 23, 26, 37, and number 39. And again, I do have your test scores available in Blackboard. And if anybody has questions, I will stick around. Otherwise, we'll pick up next time on Thursday. All right, have a great day.